All right. Good evening, everyone. I welcome you to the sixth problem-solving session of this course, Aeroengine Gas Turbine Cycles by Professor Chetan Mistry. And uh, I thank Krishna Kumar for joining. So hopefully more students will join. If not, this video will be available to watch it in YouTube. So you can go over the video recording. Okay. So So we so this is sixth week. So we are almost completed 50% of the content of this course, and it is a good idea to go and revisit what have we done because a major portion of this course content has been covered. So it's a good idea to go and revise once, revisit once. Uh, and anyway, we are actually using all the fundamental uh, concepts that we learned in week 1 and 2 in subsequent weeks. So please make sure that you understand everything properly, at least until week 6. And moving forward, it would be easier for you to quickly grasp the concepts that is going to come in upcoming weeks. Having said that, this week I hope you all must have gone through the lectures. This week what we did is turbofan engines, especially the two-spool turbofan engines. And I will be giving you a quick recap of what we did in week 6 lectures. And also I will be solving a question which is nothing but an extension of one of the question which has been solved in the lectures. Okay. And which will give you which will give you the understanding between two configurations that we learned during the lectures. All right. Um, Let me go into the presentation. So we all know the turbofan engines. There are two, especially two spool turbofan engines. There are two different configurations that you can uh, design with. In the first configuration, you have fan and low pressure compressor in a in a spool connected to a low pressure turbine, and there is a high pressure turbine which drives the high pressure compressor. That is a configuration that we have for the uh, for that is one of the configuration that you can have for a two spool turbofan engine. Um, the other configuration could be a fan can be run by the low pressure turbine, and the compressor can be run by the high pressure turbine. So those are the two configurations that we especially saw in this week. And the first configuration is looks something like this. As I said, the components driven by which spool is what determines the configuration, and we will see what are the effects of this in terms of performance parameters or other station properties in our entire gas turbine cycle analysis. So in the first configuration, as I said, you have a, so let me see if I can, yeah. So I think you will be able to track my mouse, or maybe I can use pencil. So in the first configuration that we have here, we have this spool, a light gray spool over here, which is driving, this is the low pressure compressor and fan, right? Which is driving low pressure compressor and fan. And this dark spool over here is driving the high pressure compressor. So basically the work is coming from the high pressure turbine. So that is the thing. And as every gas turbine cycle, you have a inlet and a fan. There is a two streams going. After the fan, there will be two streams. The entire air stream is divided into two streams. One is a core stream, and there is a bypass stream. And as it goes in the core stream, it encounters compressor, combustor, turbine, and nozzle. When it goes in the bypass stream, it just encounters a nozzle, gets expanded, reaches a higher velocity, which gives us thrust. So there will be two thrust components, which we already saw in the last week of turbofan engines. And remember, this is the unmixed flow. There will be a mixed flow turbofan engine, which you will soon learn it in upcoming weeks. Okay, so the first configuration is fan and low pressure compressor driven by the low pressure turbine, and high pressure compressor driven by the high pressure turbine. This is the first configuration. And if I want to draw a TS diagram for this, you have P infinity line isobar over here. This blue color is a P infinity line, and initially at the inlet, your air gets compressed to P02. uh, Imagine it is flying at certain Mach number. Okay, uh, and after from the inlet, first it gets compressed in the fan. Okay, so the entire air stream goes through the fan. So from 2 to 10, there is a component fan, and across this there's a pressure rise from P02 to P010. And then you have then we are following the core stream. We will come back to bypass stream. In the core stream, what you have is you have low pressure compressor. So from 10 to 3, there is again pressure rise, and then you have high pressure compressor, which reaches even higher pressure. And at the end of high pressure compressor, the air will be at high pressures and temperatures. High pressure. It enters the combustion chamber and fuel gets added, and during this process pressure almost remains same, but there will be a slight pressure loss in the combustion chamber. That's why P04 will not be equal to P05. And during this there is a heat addition because of the temperature rises. That's why T05 is higher than the T04. And after that you have a high pressure turbine, which and the pressure at the exit of high pressure turbine would be P06, and it encounters a low pressure turbine. Again, the pressure drops further, and during these two processes, the work is extracted, and that work is should be used to drive the fan, low pressure compressor, and high pressure compressor. And then we have a small tailpipe where the pressure losses can happen, and after 8 to 9 you have nozzle. Okay, and this is the core stream. Now in the bypass stream you do not have anything. The air which gets compressed by the fan gets expanded in the nozzle. So from uh, 10 to 11. Okay, 11 is the exit conditions of the bypass stream. Okay, so this is for the configuration 1. And the configuration 2 would be something like this. Here you can see this gray spool, which is driven by the low pressure turbine, and it is driving only fan. It is not driving the compressor. Previously it was driving a low pressure compressor also. And there is this black spool. um, Here this black spool is actually driven by the high pressure turbine, and it is driving the compressor. Okay, here we don't separate it as a low pressure compressor and high pressure compressor because everything is in the same spool. So it's just a single component compressor. Okay, and although the number of stages would be different, so that you can clearly see. Anyway, we are not interested in number of stages. We are interested in the overall parameter, pressure ratios across the compressor. Okay, and you can also see there is a slight change in the station numbers, so you may need to be careful while referring to this configuration. Okay, let's look at the TS diagram of this case also. You have P infinity line, which is atmospheric pressure isobar you have, and then from there again there is a uh, inlet to P02, and then you have fan across which the pressure rises from 2 to 3. Okay, uh, previously we saw it's 2 to 10, now it is 2 to 3, so there is that change. And from T there is a two streams dividing. One is going through the core section, and one is going through the bypass section. And uh, the air which goes to the core region or the core stream will encounter the compressor. Now it is a single compressor, not a low pressure and high pressure compressor. So you will have a very big jump in pressure. And After that, you have combustor, across which there can be a slight pressure loss, but it is a constant pressure. You can say almost a constant pressure heat addition process. Um, and then after combustor, you have a high pressure turbine from which work is extracted and used to drive the compressor. And you have low pressure turbine, which is used to drive the fan. Okay. And then again, you have a tailpipe and then nozzle. Now, this nozzle is in the turbine exit nozzle, or you can say core stream nozzle. And you also have bypass nozzle, and the station numbers would be from 3 to 10, across which the pressure drops. During this process, velocity increases, which is going to generate thrust. So the thrust would be calculated for both core stream and bypass stream, and the bypass stream you should calculate V10, uh, rho 10, and T10 in order to find the thrust. Okay. Similarly, for core stream you need to calculate V9, T9, and uh, rho 9. Okay, or P9. So this is the question I have today. This question we have already seen in the lectures. So there is a engine which is currently at the sea level. It is not flying, so Mach number would be 0. The engine speed would be 0. And you have atmospheric pressure and temperature, P infinity and T infinity given. Fan pressure ratio is given. Low pressure compressor, high pressure compressor ratios are given. Bypass ratios are given, which is 9. And turbine inlet temperature is 1600 Kelvin. Total pressure loss is 3%. And then core engine mass flow rate at 138 kg per second. So you have seen this question. It is in the lecture, but we solved it only for one configuration, which is fan and low pressure compressor driven by the low pressure turbine, while the high pressure compressor is driven by the high pressure turbine. Now in this class, what we are going to do is we are going to try the same numbers with the same numbers. We are going to, let's say, if I design in such a way that fan is driven by the LP turbine and compressor is driven by HP turbine, how these important performance parameters going to change. For example, engine exit velocities, thrust, TSFC, area of the nozzle, and efficiencies. How are these going to change from one configuration to the other configuration? Basically, only the component, only the turbine, whether it is driving the fan and compressor or just the fan, is where the configuration differs. Otherwise, all the numbers are actually same. So in that way, it is a very interesting problem to see, to compare ourselves why to prefer a configuration. Okay. So these are some efficiencies and losses which we all know. We will take this into account when we solve this problem. Yeah, as I said, this has been already solved in the lectures. So let's go forward. So this is the first configuration where fan and low pressure compressor is driven by the LP turbine and high pressure compressor driven by the HP turbine. And we have TS diagram also over here. Okay. And for this, we have already solved in the lectures, and these are the velocities and thrust, TSFC, and efficiencies that we got. Now, what we will do, we will try to get these numbers for the configuration too. Okay. That would be the today's agenda. Let me go forward with it. So you can see until fan there's going to be not much of a difference, and after fan you have a compressor. Compressor is a single unit in the second configuration, which is driven by the high pressure turbine, while fan is driven by the low pressure turbine. That is the change, right? So from compressor there will be some difference in the calculation. So let me show you how we are going to solve this problem. So inlet you have P infinity and T infinity. Based on that you can find P02 and T02, in which in this case it's going to be same because our engine is at sea level. Okay. And then you have fan with the pressure ratio, from which we can find the P03 and T03, and it enters the, now we can find core flow parameters. In that you have a compressor. Now you can see the question has low pressure compressor pressure ratio and a high pressure compressor pressure ratio. Low pressure was 2.47, high pressure was 12. Now in the second configuration you have only one compressor, which means uh, So both the low pressure compressor and the high pressure compressor values that they have given is being done by a single component. Okay, so here you will have 2.47. First, air gets compressed to 2.47. Maybe like some stages of the compressor will compress the air to 2.47 times the pressure, and from there it gets compressed to 12 times the pressure. So basically that's why we multiply 2.47 with 12. Okay, we do not add the pressure ratios, we multiply basically. Or you can also think in terms of chain rule. So at the entry I have P03 and at the exit I have P04, and in between, let's say if I divide the compressor into two, uh, and if I say the one part is 2.47, the other part is 12, you can always find the overall pressure ratio by just multiplying it, because P03 by P intermediate times P intermediate by P04 is what they have given. So if you want to find P03 by P04, you just need to multiply these two parameters. Okay, so here you have one single compressor, that's why you need to multiply these two pressure ratios. That is one small change compared to whatever we solved in the lecture. And then you directly have a combustor in which you are adding fuel. You need to find fuel air ratio, which is F, and also you need to find exit pressure. The exit temperature we already know, it is defined by, it's a parameter, it's a design parameter, it is defined uh, while we are designing the cycle itself. And then you have HP turbine, which drives the compressor, and from this energy balance you can find P06 and T06, and then you can give that to LP turbine, which drives the fan. So this energy balance you need to take care in order to find the exit parameters of P0, like LP turbine, which is P07 and T07. And then you have a tailpipe where there are no losses, and then you have nozzle. This is in the core stream. Now in the bypass flow, you have fan, from which the air from the fan gets expanded in the fan nozzle, and then you have few more parameters to calculate. Once you have these green parameters, you can find out the uh, performance parameters basically. Okay, let's go forward with the component wise. Let's go forward. First is inlet. Inlet, as I said, M infinity is 0. The engine is stationary, and if that is the case, we all know P02 and T02 will be same as P infinity and T infinity. So you can also substitute M infinity in the equation that you have, isentropic flow relation. So that will lead to this. Okay. So P02 and T02 is same as P infinity, which is 1 bar and 288.15 Kelvin. Okay. The next component that we have is fan. Uh, the fan pressure ratio is 1.36. It has been given. So from 1 bar, it has to get compressed to 1.36 times the 1 bar, which is would be 1.36 bar basically, which will come out to be 137.8 kilopascal. Okay. Sorry, 1.36 atmosphere. I might have misspelled it. So P03 would be 1.36 atmosphere, which corresponds to 137.8 kilopascal. And then you have to find the temperature at the exit of the fan, and you also have fan efficiency. Okay, this is not an ideal case as we saw in the last week, where we really solved the ideal turbofan engines. But here it's a real turbofan engines. We are going back, and the efficiencies is also given. So the efficiency of fan is 90%. So if you substitute these numbers, you will get T03 by T02, and this also we solved it in the class itself. It is 1.102, and if you substitute T02, which is 288.15, you will end up having 317.55 Kelvin. So this is the pressure and temperature which is at the exit of the fan. Now the stream has divided into two. Okay, one goes through the core stream and the other goes into the bypass stream. In the core flow, this is what we saw. So we had two compressor, as I was telling before. In the configuration one, we had low pressure compressor and we have high pressure compressor. Okay, and we solved pressure and temperature separately for these two compressor. Now we have only one compressor whose pressure ratio is different, which is 2.47 times 12. Okay, and if you we can use this numbers to find pressure. So P04 by P03 is given. 2.47 times 12 would be something like 29. and if you multiply that with P03, which was basically 137 kilopascals, it will come out to be for 4084.45 kilopascal, which is around um, 40.84 bars. Okay. um, and then you have you can note something here. So I have 40.84 bar over here, and what I also have is low pressure compressor pressure would be 340.37 bar, and after that it goes through high pressure compressor, and there also you end up having 4084.44 kilopascals. Okay, so this also could be 44. It's just a round off thing. So you will end up having the same pressure ratio, although here you are solving it as a two different compressors. Here you are solving it as a one compressor. You will still have the exit of the compressor stage would be, or you can say at the exit of both the components, the pressure would be 40.84 bar. Okay. um, let's go forward. Now you have a temperature again. We know the relation from where it is coming. It's from the isentropic efficiency relation. You can derive this. uh, we have seen this multiple times, so I'm just stating you the formula here. Now you can substitute this pi c here. Pi c would be 29.64, which is nothing but 2.47 times 12. Okay, so 2.47 times 12 is 29.64. So that is what you will see over here. And if you do that with the isentropic efficiency of 87 percentage for compressor, which is what we used, you will end up having uh, temperature ratio of 2.8776. Okay, so let's see what is the exact exit temperature of this compressor stages. So that would be something like 913.78 Kelvin. Okay, so um, so there is something you can note here. The temperature at the exit of this whole compressor stage is 913.78 Kelvin, while the temperature at the exit when you divide it as a two compressor is 930.41 Kelvin. Okay, so you can think why there is a difference between these two compressor. Um, yeah, maybe I will let you think about it, and if you find the results, please share it with me. So there is some small difference between these two things. That's why you see these differences. Okay. All right. So let me give you one hint. You may be little. So you have a efficiency for a low pressure compressor. You have efficiency of 0.87, and you have for high pressure compressor you have efficiency of 0.87. Okay, so it has to do with efficiencies. Okay, so if you think in that manner, you will be able to find the reason why you have a different temperature when you consider these two compressor as a single entity, and when you consider this compressor as a separate entities, why you have different temperatures, that you will know. Okay, although the pressures are same, when so at the exit of this whole compressor component, the pressure of the air which is going to enter the combustor is same, which is 40.84 bar, but the temperature with which it enters is different for these two cases. So, and that has to do something with efficiencies. So I will let you think a little bit about it. I'm sure you can find the answer for this. Okay. All right. Anyway, going back, you have the temperature to be 913.78 Kelvin. Okay. The next component that you have is combustor, and in the old configurations, what we saw was this is the fuel air ratio, and this is the pressure that we uh, sorry, this is the pressure that we found for this case. Now, um, for this, there is a pressure loss of 3%. Okay, the same pressure loss that we are taking here, there is a pressure loss of 3%. So then again the pressure would be same. right? So again, because the entry pressure is same for both the cases, and there is a pressure loss of 3%, so the exit pressure of the combustor will be same as whatever we found in the previous configuration also. So in that way you can relate. So pressure is not getting affected, but the entry temperature of combustion chambers are different. So and but the exit temperature has to be maintained at 1600 Kelvin. So that is the important thing that we saw, right? So turbine cannot handle more than 1600 Kelvin, at least for this problem. That's why they give it as a design parameter. So the exit temperature cannot exit 1600 Kelvin. So if 1600 Kelvin is the exit temperature, the inlet temperatures are different for these two configurations. By now you can guess what would be coming as, what would be the difference, right? Let's go forward. You have energy balance, you can do energy, so you have to do energy balance to find the fuel air ratio. So here what you have is m dot core cpc t04, which is the entry energy of the air, and then you are adding some fuel to it with some heating value, and that will be equal to whatever the energy with which it comes up. That's what energy in is equal to energy out. So here the energy in would be the energy of the air plus the fuel energy with some burner efficiency, which is 0.96 that we have. And then you have CPC and CPH. We all know why, because composition changes, specific heat changes when at the exit of the combustor. Okay. Now, if you rearrange this, you will get the fuel air ratio equation, which is similar to whatever we saw here. Both are same, and if you substitute all these numbers over here, only thing is here you have 930.14, but here you will have 913.78, and this will cause an increase in fuel consumption. So you can see that you have 0.02324 for this configuration, because your entry temperature was um, little lower than the previous configuration. So you have to put extra energy in terms of fuel in order to reach 1600 Kelvin. That's the logic behind it. Okay. I hope this is also clear till now. Now let me go forward with the turbine. Um, So from turbine, it's a bit different. So I would like you to take your pen and paper to solve it. Until here, it's a straightforward thing. From turbine, your energy balance is going to change. Okay, because um, in our configuration one, a high pressure turbine drives only high pressure compressor. Now, it's not that just that case. High pressure turbine drives the whole compressor. Okay, so in the previous case, the high pressure compressor has a pressure ratio of 12. Here, the compressor has a pressure ratio of 12 times 2.47, which is like 29.43. We just now saw in the compressor section. So this change will lead to different exit temperatures and pressures, which is going to be different than whatever we saw in the configuration one. Okay, so as I said, the energy balance would be the amount of work extracted from the turbine when it is extracted from the HP turbine, which is going from T05 to T06. Okay, so from T05 to T06, you have the mass flow rate is mass flow rate of core plus the fuel air ratio. So that's why you have m dot core into 1 plus F times CPH. Okay, CPH is for hot gases, and T05 minus T06 is the amount of work extracted, and that is used to drive the whole compressor. In our case, it's T04 minus T03. Although the numbers here may look same, but these two equations are not the same. They are not same. Okay, because the numbers are different. The station numbers are different. Station numbers are different. The equation might look same, but they are not same. Okay, so please be careful, and hence you will have different temperatures which we found out. So you can rearrange to get this formula which we know, and you can substitute these numbers. So if you substitute these numbers, um, can you guys calculate and tell me what would be T06? So T05 would be, so T06 would come out to be 1089.45 Kelvin. Okay, this is the HP turbine exit temperature. Okay, which has driven whole compressor. So ideally, what would you expect? Will the temperature should be increased or decreased? So you can clearly see that the turbine exit temperature for the configuration 1, which was driving only the high pressure compressor, was higher, while the number that we currently found out, which is driving the whole compressor, was lower, which means we are extracting more energy out of it. So that's why from 1600 Kelvin, it has to go through a lot of reduction in temperature, and then only it can supply enough work to the compressor, because the compressor has to compress 29.43 as the pressure ratio, but here it has to compress only 12. The pressure ratio to of a compressor here is only 12. So that's why you please note that the pressure and temperature which enters the HP turbine is same for both the configuration. Okay, pressure and temperature enters the HP turbine is same for both the configuration. There is a slight difference in mass flow rates. So before it was 0.00228 is the fuel mass flow rate that you added. Here you are adding a little increased amount of fuel, but you are driving a bigger compressor compared to the configuration 1, and that's why you have a lower temperature, which is 1089.45 Kelvin. Okay, I hope this is clear. Now let's move forward and find the pressure. So we also need to find the pressure. We found the temperature. Now to find the pressure, you have this isentropic efficiency relation. So from there you can get this relation. Again, as I said, these two are not same. They are not same. Although the numbers may look same, the variable is may look same, but they are not same. So please be careful about it. So um, the turbine efficiency is 94%, and we know T06 features found out 1089.45 Kelvin, and the hot gases has specific heat of 1.33. So till now we used 1.4, now it is 1.33. So if you do this calculation, you get about the pressure drop across the HP turbine is around 0.188. So again, this also proves that ideally this should be lesser than whatever the pressure drop that we see in the turbine in the configuration 1, because it is driving a low pressure, it is driving a lesser pressure ratio compressor. Okay, and hence that is actually clearly visible. You have 1.88, and here you have 0.2547. Okay, so which leads to a lower pressure here, which is around 744.8 kilopascal, while the HP turbine exit pressure is 1008.94 kilopascal. Okay, so this is the major difference. You will have lower temperature and pressure at the exit of the HP turbine when you go from configuration 1 to configuration 2. Okay, I hope it's clear till now. I hope everyone is on the same page. Again, if you have any questions, please stop me anytime. Uh, Let me move forward with the LP turbine. So now, again, the LP turbine is different. So what happens in a LP turbine for the configuration 1 was, you can see, the LP turbine was driving both fan and LP compressor. Okay. Uh, Now LP compressor is already driven by the uh, HP turbine for our case. In fact, there is no LP compressor in our case. It's a single component compressor. Now the LP turbine will be driving only the fan. Okay. So that is the energy balance that we have here. This is the work extracted from the LP turbine. You can see from T06 to T07, and this is the work you know, um, given to the fan. So again, there's one important thing. We are assuming there is a mechanical efficiency of 100%. We are not assuming there's any losses in the spool. Okay, in there could be losses in the spool also. When you have, you need to account that efficiency factor also in this equation, energy balance. Okay. Uh, yeah. So you can note that you have m dot core plus m dot fan, because the fan actually sees the whole uh, what you call the mass flow rate, which is going to be both core stream plus bypass stream. That's why you have m dot core plus m dot fan. So you can rearrange this equation also. Um, I think probably there is a mistake. There should be 1 plus beta here. Okay, there should be 1 plus beta over here. I will recheck this equation. But anyway, uh, if you substitute these numbers, you will end up having a temperature of 837.7 Kelvin. Okay, you can see that there is a temperature at the exit of the turbine, LP turbine, is a little higher than the temperature at the exit of the LP turbine, which we saw in the configuration one. Okay, so these are the important changes. Now let's go forward with the uh, pressure. Let's find the pressure for LP turbine. So once again, did I take 1 plus beta into consideration here? Let me quickly check. Can one of you try to do this calculation? Maybe you may need to. So what I'm trying to say is, you need to add 1 plus beta over here. So if you add 1 plus beta, you will have 1 plus 9 over here. So I just want to make sure whether the temperature that we have is right. I hope it's just a typo. I didn't make any mistakes while calculating this. So if any one of you have answer, please let me know. Into what was T06? Sorry, this is also wrong. T064108.9 Kelvin. Yeah, I guess it is right. Okay. So this is the change that we have here. So it's just a typo. I will correct it. Let me recheck it once. Give me a minute, guys. Sorry about that. Share screen. Yeah. All right. So yeah. So actually, I've solved it here, uh, where we have 1089.45 times 1 plus 9, which is beta, and then you have 1005. The same equation, When you solve it, you will get 837.7 Kelvin. So that's what this is here. So it is right. So there's some small typo mistake which I will correct it while I post this notes. Okay. Anyway, let's go forward. You have found the temperature at the exit, which is around 837 Kelvin, right? Now you need to find the pressure also at the exit. So in the pressure, we already found out the pressure at LP turbine at the exit pressure was 221.462 kilopascal. Okay, and let's see what would be the pressure. So if you want to guess, uh, would the pressure be same or would it be different? That is something you need to think about. Okay, so ideally you see you have compressor, you have two compressors, although but the compressor pressure ratios what you are solving for the compressor is same for both the configurations. So the turbine, which is what is giving the uh, what do you call the energy, should also run with the same thing. In fact, the entry pressure and temperatures for the turbine, for the both HP and LP for the HP turbine basically is same in both the configurations. So ideally, you would expect the exit pressures to be same for both of this configuration, but let's see what happens. Okay. So again, we know from the isentropic efficiency relation, you can get this equation and you can substitute these numbers which we found till now. And then this will lead to a pressure of 238.89 kilopascal. Okay. The pressure at the exit of the turbine, LP turbine, is a little higher than the configuration one. Okay. So you can try to find the reason behind this. If you think a little bit, if you go through a little bit thought process, you will able to find out the reason. Why would it actually do this? Okay. Think in terms of energy. What is changing in terms of energy? So we are adding more fuel, and because of that, you have higher m dot of m dot f also. So um, you will have some difference in your pressures. Whether it will increase or decrease, if you go through this thought process, you will know. Okay. All right. So this is the difference. You have a difference in pressure from LP turbine exit pressure. Okay. Let's go forward. The the final component that we have in the low pressure in the core stream is the nozzle, and first to and before that you have tailpipe, but there is no losses, so you have pressures and temperatures will be same, and then you have nozzle, and the nozzle inlet is 238.89 kilopascal and temperature is 837.7 Kelvin, which is a bit different than uh, the turbine nozzle that we saw in the configuration 1. So first we need to do check for choking condition, and the choking condition however will be same because it is going to depend on only gamma and efficiency of nozzle, which is we are which we are taking to be same 95% efficiency. So you can see that this is also 1.917, this is also 1.917. Now however the P08 is different for different for these two configurations, so your critical pressure would be different. So if you calculate that critical pressure, which is coming out to be 134.63 kilopascal, and we are at the ground whose atmospheric pressure is 101.325, and this pressure is a little higher, so which means your nozzle is chocked and your exit velocities corresponds to Mach number equal to 1. Okay. Yeah, basically you have pressure at the exit of the nozzle. This is the static pressure P9, which will be 124.63 kilopascal, which is actually higher than the configuration 1. Okay, which was 115.54 kilopascal. Okay, all right, let's find the velocity, and the temperature ratios, again the temperature ratio will be same because that just depends on gamma h, which will be 1.165, while the absolute temperature of the exit at the exit of the nozzle will be different because the inlet temperatures are different. So which is around 719 point Kelvin, which is a little bit higher than the configuration 1, and hence this is higher the velocity again will be higher than the configuration one. So the exit velocity, turbine exit velocity is turbine nozzle exit velocity is 523.9 meters per second for our configuration, compared to whatever we solved in the lecture, which was 519.32 meters per second. Okay. Now we need to do the similar process for bypass flow. While in the bypass flow there is no change, the fan has the same pressure ratio for the both configurations. So ideally you will have no change in the calculations of fan nozzle. So that's what we will see here. The choking condition again will remain same because it depends on gamma and efficiency, which is same for both of these cases. And the fan exit uh, pressure and temperature of the fan is same for both the configuration, because the engine is at the same place and it also has the same fan pressure ratio, both the engines. Okay, and hence it is we saw it's a unchocked nozzle because the critical pressure is less than the uh, 101,325. Sorry about this that. Okay. um and then you have, hence it is less, hence the nozzle is unchocked, your exit pressure would be 101.325 kilopascal, which is same as the ambient pressure. uh, yeah, there is no change in the fan nozzle. So similarly you can find the temperature, again ratio will be same. The temperature at the exit also will be same, and also similarly the nozzle velocity you may need to find out using uh, a different formula, which is because your exit nozzle because your exit velocity is doesn't correspond to Mach number equal to 1 because it is not chopped. Okay, and that's the reason you have a different formula for velocity here. And but basically this is from isentropic flow relations if you think about it, and hence you will have velocity to be same, exit velocity of fan nozzle will be same. So there is nothing change in the exit there's not much of a change in the bypass stream. In fact, there is no change in the bypass stream from configuration 1 to 2, but there is going to be a change in the core stream, which is going to affect your performance parameters. That is what we are going to see now. First, we have area of the nozzle. Let's find the area of nozzle of the turbine nozzle exit, the core flow nozzle area. It is coming from the mass flow rate equation. We all know m dot is equal to rho a v. You have 1 plus f because that is the entire mass flow rate go like getting accelerated in the nozzle. So if you rearrange this and include ideal gas relation P9 by RT9, you will end up having these numbers. And if you substitute, you can find that the area is 0.446 meters square. Okay, while the area that we have here is 0.477 meters square. Okay, so the area has been reduced a bit. Okay, the velocity has increased, area has been reduced, and also in fact actually what you see is both density and velocity has increased, which caused the area to reduce, although there is a slight increase in mass flow rate. You can see the mass flow rate, there is a slight increase because of the fuel, because of more additional fuel that we are adding. Okay, even though we are adding that, we would expect area to increase, but the velocity and the pressure increase lead to uh, lead to a very higher effect compared to the increase in mass flow rate, which causes the area to reduce. Okay, it was 0.446 meters square. Now in the bypass flow, again as I said, there is no change in the bypass flow, so you will end up having same area as 4.53 meters square, which is same as what we saw in the lecture also. Okay, I hope it is clear the reason why these are two different things, and why the bypass is not, why the bypass is same. Okay, all right. Now the next is thrust. Okay, so the thrust, the equations are same. You have two thrust, one is core thrust and the bypass thrust. In core thrust you have both momentum and pressure thrust. That's what you see in the first line, and then you have you have bypass thrust also. So here again, if you substitute these numbers, you can calculate, and you would end up having something like 364.85 kilonewton, which is a bit higher than whatever we saw in the configuration one, which was 360.56 kilonewton, which is basically makes sense. The reason is, in bypass stream there is no change. The thrust will be remaining same, but in the core stream you have increased pressure, also you have increased velocity. So the increase in velocity actually causes an increase in thrust. So that's why you see a increase in 36 increase in thrust of like some percentage, a slight increase, although it's not a big deal. It's a 364.85 kilonewton. Okay. And similarly you can do TSFC calculation, and in TSFC we already know it's very easy to predict by now. We are using more fuel. Okay. So whether the amount of fuel that we add, is it justifying the amount of thrust that we generated, is what is uh, given by TSFC. Okay. So in TSFC calculation we will get to know whether it is fuel efficient or not. And you would see that there is a slight increase in TSFC, which means that the amount of fuel you are adding is not really fully used, fully, it's not fully potential, or it is not fully as efficient than the configuration one. Or the amount of fuel that you add, the effect of fuel that you add is more than the increase in the thrust. So ideally I would say, so the reason why I'm giving this explanation is it's very simple. The TSFC, you have m dot f increased, thrust also increased. Now whether the effect of m dot f will take over the effect of thrust is what will determine whether TSFC will increase or decrease. Okay. Now it turns out that m dot f, effect of m dot f, increase in m dot f, is taking over the effect of increase in thrust. So uh, hence leading to the TSFC increase. Okay. You can see that there is a change in TSFC of about, like, although it's very minor, but there is an increase. That's what I wanted to say. All right. And the final is thermal efficiency. We are not getting into propulsive efficiency and overall efficiency because it's a ground engine. We have thrust, we have V infinity to be 0. So propulsive efficiency will obviously be 0. But it's better for you if you write the equation and then see for yourself. Okay. So I'm not going over that. The thermal efficiency, we all know, this is the total power from the aircraft, and this is the additional kinetic energy wasted in the thing. So which means this is the total energy that has been added to the incoming air, and then that is coming from the fuel. That's why you have m dot f by qr in the denominator. So if you substitute these numbers, what do you guys expect? Do you expect the efficiency to increase or decrease? Can you guys guess? So there is an increase in thrust, and but also there is an increase in fuel consumption. Okay, so both of them actually led to decrease in thermal efficiency, because it's always the fuel consumption effect will try to overcome the thrust effect, because fuel is only giving you the power and there's going to be losses from fuel side. So you can we can think in that lines also. Okay. So at the end of the day, basically the thermal efficiency is decreasing. That's what we see here, which is around 37.01%. Okay. um, Compared to 37.48%, but it's also not that big of a difference, you can say. All because of due to the design parameters are almost same for both the configurations. Only thing is whether the spool is driving the HP compressor, or is it driving only the fan, is what is whether, yeah. So whether the spool is driving both LP compressor and fan, or it is only driving the fan, will make this minor changes. Okay, let's look at in a very holistic point of view what we did till now. uh, we had two configurations, where this is one configuration one, where low pressure turbine is driven by fan and low pressure compressor, while the high pressure turbine is driven by the high pressure compressor. Okay, and there is a configuration two which we solved today, where fan is driven by the low pressure turbine, and compressor is driven by the high pressure turbine. So I have listed down um, mm, the important performance parameters that we got for these two configurations. This we solved in the lectures, this we solved today, and we can see that there is a small change in the exit velocity. It's not by much of a change, 0.89 percentage, less than 1% change in the exit velocity. You can see less than 1% change in the exit velocity. There is no change in the bypass stream. That's why you see 0 and 0 over here. There's no change in the bypass stream. There's the nozzle exit velocity also doesn't change. The exit area also doesn't change. All right. There is a reduction in, you know, exit area, which is around 6.5%. 6.5% of the exit area on the core stream. Nozzle exit area for the core stream has reduced because of this increase in velocity and pressure. Okay, and there is a slight increase in thrust that you can see, 1.2 percentage, and there is an increase in TSFC. Both you can see around 1.1 percentage, 1.2 percentage. Okay, so all these numbers are very small. It may not make much of a difference in practical scenarios, but you can understand the concepts behind this when you go from one configuration to other configuration. Okay, or the efficiencies, there is a slight change of 0.5 percentage change in the efficiency. The configuration one seems to perform better compared to configuration two in terms of efficiency. Okay, all right. So um, so the bigger picture is, you can, a two spool turbofan engine can be constructed in two different ways, and constructing in these two in a two different ways will lead to changes in your performance parameters. Although for this case it may not be that much different, but you should be a little careful and you need to go through the calculations once again. Okay, that is the broader perspective of this session and also of this problem. Okay, are there any questions?
No, sir.
Okay, thank you, Vadapalli Madesh.
Yeah.
So yeah, so that is what I have for today. um, so if you have any questions, you can stay back and ask. If not, we will meet again in next week.
No, sir. As of now, I have no doubts.
All right, Madesh, thank you very much for joining.
Yeah. Thank you, sir.
Okay, see you next week.
Yeah, okay.